All right, welcome back, ladies. So sorry about all the emails yesterday. I thought I didn't record the lab session, but I saved the PowerPoint there, and then it turned out I actually did record the lab session. So just getting old, I guess. So anyways, so let me share my screen here. So start off with a couple reminders / announcements. So first part is reminder that the next exam is Wednesday, so 1 week from yesterday. So that's going to be over Chapter 18, which we are finishing up today, as well as Chapter 19, which we'll probably start a little bit today, and then work on that the rest of the time. So announcements to go on top of that, the examples for exam 3, as well as the extra credit. I posted those this morning, so they are now available on Blackboard, so you can start working on those. And just the other announcement is we are halfway through yesterday. We made it halfway through the class. So we are now halfway done. So we've already made it halfway through this class. So not too bad. Summer always goes by ridiculously quickly. So good. So let's pick up where we finished, which we were talking about. Move you guys down here. There we go. So we were talking about drift velocities and current densities and all that kind of fun stuff. So let's do another example involving that. So this says near the surface of the Earth, or at least near the Earth anyways, the density of protons in solar winds, which is a stream of particles which are given off by the sun. I'll explain how that actually works in a second. Has a number density, which is 8.7 per centimeter cubed of particles. And their speed, which in this case is talking about their drift velocity, is 470 kilometers per second. So it wants to know, for part A, find the current density of these protons. And then part B, if the Earth's magnetic field did not deflect protons, which we'll talk about when we get the magnetic fields, what would be the current on the surface of the Earth? So this is what we want to know. So basically, what is solar winds? So solar winds are, what happens is magnetic field lines inside of the sun. So if this is the sun over here, what happens is magnetic field lines will actually burst through the surface of the sun, creating what are known as promenades, which come out through the surface of the sun and then basically go back in. And as it does that, it strips basically protons inside of it as this thing explodes off through the surface of the sun and then goes back into the sun. So this is actually the sun's magnetic field line. But what happens is if the promenade actually gets too big, these magnetic field lines will actually cut, which basically means that it actually splits. And what it does is it actually sends out charged particles from the sun, typically in the form of protons, which then go off in all kinds of different directions, but in one direction will be towards the surface of the Earth. So here would be the Earth. So this is what we call a solar wind. So basically solar winds then are charged particles which are being sent towards the Earth from the sun's magnetic field, basically ripping out stuff from inside of the sun. Okay. So what we're told here is that this has a number density, which is 8.7 per centimeters cubed. So this is our number density. We're also told that this has a velocity, which was 470 kilometers per second. 470 kilometers per second. So the first thing it wants to know is, for part A, what is the current density? Well, we know the current density, based off what we talked about before, is the charge of the charged particle times the number density times the drift velocity. So in this case, our current density, so the current density of here is just going to be the charge of the protons, which is the fundamental charge, times this guy, but now this guy we're going to have to put into meters cubed. So this is going to be 8.7 times 10 to the minus 6 meters cubed. So per meter cubed. Good. Times the speed here, and the speed has to be in meters per second. So it's going to be 470,000 meters per second. It's going to be 470,000 meters per second. Good. It's okay. So my current density then is, when I multiply everything out, that's on my phone, That works out to be 6.54 times 10 to the minus 7 amps per meter cubed. And remember that Q here, or E, is 1.602 times 10 to the minus 19 coulombs. So that's E. So part B then says, okay, so let's say the solar winds come here and the Earth's magnetic field doesn't exist. So the Earth has its own magnetic field. It basically does this. And the point of the magnetic field, as we'll talk more about later, is that it actually deflects most of these particles. So what's going to happen is a lot of these particles get caught up in the Earth's magnetic field, and some of them will actually spiral down towards the poles of the Earth's magnetic field, which actually creates the aurora borealis. And we'll talk about that when we talk about magnetic fields. But basically what this does is the Earth's magnetic field actually causes these charged particles to deflect, and then causes actually this portion of the tail to get really drawn out in this kind of direction. But what keeps us from getting scorched basically by the sun from these charged particles is actually the magnetic field of the Earth. So what this is saying is if the magnetic field of the Earth didn't exist, then what is the current from these charged particles on the surface of the Earth? Well, we also know that current, based off of drift velocity, is the charge times the number density times the drift velocity times the area, but that's the same thing as simply the current density times the area. So here, this is just going to be equal to the current density, which we just calculated, times then the area. Now the question is, which area do we care about? So if I have basically a current, so here's my current going in this direction, here's the Earth, do I care about the surface area of the Earth, or do I care about the cross-sectional area of the Earth? So which area do I care about? Do I care about the surface area of the Earth? So is that what this is going to see when the current is coming through, or is it going to see the cross-sectional area of the Earth? So the question is, which area is this? Is this going to be surface area, or is this going to be cross-sectional area? So which area do you think it's going to be? So again, I have basically a beam of charged particles, which is acting as a current, interacting with a sphere. This is not quite a sphere, but let's pretend it's a sphere. So it's coming in and it's hitting the sphere. So is it going to see the total surface area, the fact that this thing is a sphere, or is it only going to see the cross-sectional area? So which area do you think it's going to be?
The surface area?
Almost.
No?
I was thinking the cross-sectional area.
It's going to be the cross-sectional area. There you go. So it's going to be the cross-sectional area because it's going to come and it's only going to hit half of the surface. So it wouldn't be the whole surface area anyways. But as it's coming in, it's basically only going to interact with the cross-sectional area, so not the actual total surface area. But, so this is just going to be, what, J times the cross-sectional area.
Down. No.
The cross-sectional area of a sphere is simply that of a circle. So this is just pi times the radius of the Earth squared.
No.
So if I look up what the radius of the Earth is, and I plug in my numbers, what I get in this case then is that the current works out to be about 8.34 times 10 to the 7th amps. Okay, that is a ridiculously huge current. Now, we kind of talked about this before. 100 amps of current through a human body would definitely kill a person. So this is what? 5 times or 5 orders of magnitude greater than that, which basically means that if the Earth's magnetic field did not exist, the surface of the Earth would basically be a fiery pit of destruction. Basically, nothing would be able to live on the surface without that Earth's magnetic field. Nice. Nice gloomy day. Okay, great. So last thing we're going to talk about in this chapter is, so we mentioned that if I had a element, so here's my element, and again, we're going to apply a potential difference across this element, which then causes charged particles to move. So now we have our J on the inside. So here's my J, which is a vector. And this happens by creating an electric field actually inside of this wire or this element. Okay? So what we want to know now is, what is the relationship between the current density and the electric field? Okay. So what I mentioned last time was that the current density will be in the direction of the electric field, but where we want to know why is that true? So how do we actually know that? And to do that, let's start off with Ohm's law. So remember, Ohm's law says that the potential, so the change in potential, is equal to the current times the resistance, right? Now, what we now know is that resistance is equal to the resistivity times the length divided by the cross-sectional area. So this has a cross-sectional area, has the length to it. So this is
Down.
We also know that the change in potential is equal to the electric field times the length. Right? Because remember that electric field, the magnitude of that is equal to the change in potential divided by the change in distance. So in this case, the change in distance is L. And we also know that the current now is equal to the current density times the area. So let's put all these things together. So the left-hand side we're going to write as electric field times the length. Oops, use the wrong length. There we go. And that's equal to now the current, which is the current density times the area, times the resistance, which is now the, my daughter's screaming, resistivity times the length divided by the cross-sectional area. So here the area is going to cancel with this area. This length is going to cancel with this length. Is equal to the current density times the resistivity. Which means that the electric field right now as a vector is equal to the resistivity times the current density as a vector. Or a lot of times what we do is we're going to define a new quantity sigma, which is equal to 1 over resistivity, which is what's known as the conductivity. So another way we can write this is we can write this as the conductivity times the electric field is equal to the current density. So either one of these two are the same thing. These two guys are what are known as the microscopic version of Ohm's law. So this is the microscopic version of Ohm's law. So what is conductivity? So resistivity is a measure of how good of a resistor an object is. So rho is equal to a measure of how good a resistor a material is, which means that conductivity then is a measure of how good a conductor a material is. So basically, notice that they're inversely proportional to each other, which means that if something is a very bad resistor, then it's a very good conductor. But if it's a very bad conductor, then it's a very good resistor. And so they're going to be one or the other one, but they're inversely related to each other. So rho is just equal to 1 over conductivity. So if it's a very bad conductor, meaning this number is going to be very small, then it has a very large resistivity, which means it's a very good resistor. But if it's a very bad resistor, meaning this is a very small number, then it's going to be a very large conductant, which means it's a very good conductor. So typically, they're going to be one or the other. So something with a high resistivity, that's something which is an insulator. Something which has a very small resistivity is something which is a conductor, which is a metal. So good. So let's use all of this and do an example. So this example says that we have 115 volts is applied across a wire that is 10 meters long and has a radius of 0.3 millimeters. The magnitude of the current density is 1.5 times 10 to the 4th amps per meter squared. We want to know what is the resistivity of the wire. Okay. Well, we now know that the conductivity times the electric field is equal to the current density, or this is the same thing as the electric field is equal to the resistivity times the current density. Okay. So from here, since it tells us the current density, it also tells us the electric field and, the potential and the length, and that tells us the electric field. So now we can easily solve this for the resistivity. So this tells us that the resistivity is going to be the electric field divided by the current density, which is the same thing then as the change of potential divided by the length times the current density. This is my resistivity. So we know that this is 115 volts divided by 10 meters times the current density, which is 1.4 times 10 to the fourth. So this gives me a resistivity of, find it in my phone. So this works out to be, when I finally find it, there it is, 8.2 times 10 to the minus 4. So it is 8.2 times 10 to the minus 4 ohms meters. So this is our resistivity. So not too bad. Not too bad. So again, this is just a relationship between the electric field and the current density. And again, since resistivity is something which is always positive as well as conductivity, what this tells us then is that the electric field is in exactly the same direction as the current density. So the direction at which the charged particles flow is in exactly the same direction as the electric field. Now again, all this is with the caveat and the fact that what we think it is that it's charged particles which are moving, and not just charged particles, but positively charged particles which are moving. It turns out in actually reality, it's actually negative charges moving in the opposite direction. So the actual motion of the particles is in the actual opposite direction, but you get an extra negative sign, so the negative signs actually cancel each other, which actually means that the current density is still in the direction of the electric field, even though the actual motion of the charged particles is in the opposite direction. Because now you have a negative charge with a negative velocity, those two cancel each other, which actually gives you the right direction. Okay. So good. So all of that together brings us to today's group assignment. Yay for group assignments. So this says that we have a potential difference of 1.2 volts applied to a 33 meter long wire of 18 gauge. So an 18 gauge just means that it's 0.04 inches in diameter. And what it wants us to do is calculate the currents, the magnitude of the current density. So what is J? The drift velocity, and then the magnitude of the electric field inside of the wire, and then the rate at which thermal energy will be lost or will appear in the wire, basically being lost. Good. So what is the power which is lost by the wire? So remember, this is either going to be I squared R or V squared over R. So either one of the two. But so good. Okay. So here you know the potential difference, you know the length. So in that case, you know the electric field. You know Ohm's law, so from resistivity, so you're told this is what, copper. So you're told the resistivity of copper is 1.72 times 10 to the minus 8 ohm meters, and the number density of copper is 8.47 times 10 to the 22 per centimeter cubed. All right. Okay. So, well, split you guys up into some groups. How many we got today? So we could do 2, if I do 3 rooms. We'll do 3 rooms today. Okay. Looks like you got to talk to yourself.
I know, I'm all by myself here.
Tara was supposed to be there, but I don't know if she lost connection or something, but yeah.
I don't know. I think maybe she had her microphone on, and it sounded like she was having trouble with her dog or something.
I thought that was Molly's actually, but
Oh, was it? Okay. Then
Yeah.
I'm not sure.
Gotcha.
I don't know. I had actually started to attempt this one when I saw that it was already up, I think
Okay.
on Monday.
Yep.
And I've gotten through part A and B. And since
Okay.
I really like it when you leave the answers that you got, so I know
Yep.
when I've done something wrong.
Yeah, if I remember to do that, I do that. Other times I'm
Yeah.
old and forgetful. So.
And I've gotten through those too. So now I'm just trying to like refresh my memory on the
Okay.
given information and then work on finding the drift velocity.
Gotcha. Okay. Yeah, so the drift velocity, you're going to use either the J is equal to QNVD, or you can use I is equal to QNVD
There
times
we
A.
go.
Yeah, so either one of those two would be fine.
All right.
All
And
right.
let's see.
Very nice. Okay, I'll be back.
He was the density. Okay.
All right, how are we doing, ladies?
I'm just kind of starting it out right now.
Very good. I'll be back.
Or two.
How are we doing so far, ladies?
Yeah, that's what I.
Good. We're on one.
Yeah,
Part A there? Okay.
Yeah.
I'm trying to multitask here, so.
I see. You're out for a walk? Walking the dog?
Yeah. Yeah.
What kind of dog is it?
She's a Cairn Terrier.
Okay.
Times the
Ah, there you go. Okay. Very nice.
Oh, crud. It's in inches.
We had to convert that, right? Yeah.
Yeah.
Yes. Yeah, you got to put that into meters. So the conversion should be 10 to the minus 6.
Okay.
Oh, in inches. Sorry. No.
Yeah.
Look it up. I
It's
forgot.
like,
I think it's like
0.
40 inches in a meter or something.
Yeah. so I think
I was
it's like
thinking of the,
0.0254 meters, right?
Sounds about right. Yeah. Sorry, I was thinking about the number density. You're going to have to convert that into meters cubed as well. But yeah, so inches. So how many inches was it?
Wait, did I?
4. Okay.
We have to use the number density?
When you're trying to get the current density. Yeah, so not for part
Oh,
A.
so not the, okay. I thought you were talking about A. I'm just on A, so.
No, not yet.
Got it. I was like, whoa.
So 0.04 inches is 0.001016 meters.
Thanks.
0.001016 meters.
0.00106?
016.
016. Okay.
Yes, there you go. Okay. How are we doing, my lone soldier?
I'm trying to resolve, is E the fundamental charge?
Yes.
I'm looking at an example problem. When I typed that into my calculator, I got a very large number that's not correct.
For which part?
For the drift velocity, I did.
Well, did you make sure you put the number density in meters per meter cubed instead of centimeter cubed?
No,
Okay.
I did not change that.
Okay. So that would be the.
That's probably where it,
Yeah.
all right.
Yeah. So there's a 10 to the minus 6 difference between
Right.
centimeter cubed and a meter cubed. Yeah.
So, again.
Unfortunately, sometimes my numbers are wrong, so you gotta check those.
Yeah, but I'm like, between the two of us, I'm not going to be like, he has to be wrong. You've been doing this far longer than I have. And I could be
True.
like, I got something different. You have to be wrong.
There you go. Well, I never claimed I could use a calculator, so.
Me neither, apparently. 'Cause, like, it was making me so nervous. It was the night before one of our tests, and I was practicing with one of the examples, and you had an answer that was different. And it took me like the math was right, but when I typed it into the calculator, it took me like 7 different tries to get the same answer. I was like, I'm doomed.
Well, if it's a calculator error, I that's only 1 point off, so don't worry about
You're like, I'm following you all the way down, and then the number you spit out is just wrong. I don't know where that came from. Nice try.
Yeah. Like I said, as long as your algebra's right. Yeah.
I'm still getting something that's way too big.
Okay.
1.56 times 10 to the negative 4th. I got 1.1 times 10 to the 42nd. That's not right. So I solved the drift velocity. I've solved for drift velocity as drift velocity equals current density over E times N.
Yes. Yeah? Mm-hmm.
And B was the current density?
Yes, correct.
So that is the little j,
That's
right?
little j, correct.
Okay.
Yeah.
Hmm.
Yeah. Okay,
So
I'll check it in a second. So, let's see here. Yeah, so let me look up, because I don't feel like doing a conversion. So I want, so
unless I did little.
So on a centimeter cubed to a meter cubed. So yeah, so 10 to the minus 6, but that's going to go to a 10 to the positive 6 because it's inversely, right? Okay, so let's do it that way. Okay. Let me pull it mathematically.
Did I go the wrong? Maybe I went the wrong way with the x.
Yeah, because it's 1 over centimeter cubed, so that means it has to increase by 10 to the 6th. So that means n is actually 8.47 times 10 to the 28.
Okay. I went the wrong way.
Yeah. Yeah, it's because it's 1 over instead of just on top, so yeah. Okay, I'll be right back. Let me go check on some of the others here.
Like finding the resistivity first. And then just
How are we doing here, ladies?
I think we just finished up the first part.
Okay. Good.
Part B then.
Right. So as long as you know the current, then the current density is just going to be the current divided by the cross-sectional area. That's right. So here you'll have to convert that diameter from inches into meters. So, yeah. Good. Very good. Back.
Wrong values. Okay.
All right. How are we doing, ladies?
We're doing good. We figured out the first one.
Nice.
Yes.
Magnitude of current density.
So part A or the whole thing?
Part A.
Part A. Okay, good. Good. So for part B, since you know the currents, you know current density is currents per area. So it's just going to be that current that you found divided by the cross-sectional area.
Okay.
So that's it. So just make sure that the inches are in meters and
Yeah, that was the fun last one.
That's a cute dog. What is that?
Yeah, she's a Cairn Terrier. A Cairn Terrier.
Hard carrier.
Mhm.
Such a different color.
Yeah, she is.
Pretty.
E equals 1.2
All right.
volts.
Did you check the number? Is it out? Did it come out right this time?
Yes, I figured it out. Not only was I the wrong way on the exponent, I needed another set of parentheses because it was doing the first two numbers divided by each other and then multiplying by the third one,
Yeah.
which is how I ended up with this huge number instead
Yes.
of a really small one. I was like, if those two are both in the denominator, it should be really small because there's a huge number on the bottom. So I have to be really careful with my parentheses, apparently.
Unfortunately, yes.
So now I'm doing D, which is the magnitude of the electric field in the
And
wire.
that's just the potential divided by the length. Yeah.
Yep, that's where I was headed.
Okay.
So that's good. I think I'm doing okay.
Good.
I seem to understand like circuits and stuff better than sound wave. The waves were hard for me, especially because we would have like what's happening with a single particle, what's happening with the whole wave, and I'm like, oh boy.
Yeah.
That was hard for me. So I'm
Yeah.
hoping that this will be a little bit better.
It is.
The fact
And
that it's accelerated makes all of it hard.
Yeah, all of this exam is usually it's a lot easier because yeah, it's a lot more just kind of plug and chug and kind of things like that.
I don't know. I'm not so good at that as we found out. It's just like everything when you're grading the papers, just mark it wrong and put parentheses. In the calculator, use your parentheses.
That's right. That's right. Yeah, I'm sure you're not the only one, so it's fine. Nice. All right, let me go check on everybody else.
All right, sounds good.
Who's the last one I checked on? Okay, go back. It's me again. How we doing?
Good. We're working on C right now for the drift velocity.
Good. So drift velocity, you can either use the current or the current density. Either one is fine. If you use the current density, then remember the current density is equal to the charge times the number density times the drift velocity. So since you already know the current density, the charge is just the fundamental charge. So E, and then the number density is already given to you on the bottom. Just make sure you convert that into meters cubed instead of centimeters cubed. Then you can use that one, or you can use the current. The only thing that's different is now you have to multiply by the cross-sectional area as well. So it's probably just easier to use your answer from B. So that means the drift velocity is going to be your answer from B divided by the charge and divided by the number density. One.
4, 5, 6. Yeah, that's 6.
All right. How are we doing so far?
We're on part C.
Good. Okay.
What's the shortcut or whatever with the exponent? So like 8.47 e to the 22. I know it's e to the negative 6 meters in a cubic centimeter. So can we?
Right, but that's on the bottom. So since it's in 1 over, because it's 1 over centimeters cubed, then 6 goes on top. So that means it's going to be 8.47 times 10 to the 28.
So you add.
Yes.
That's the things I forget, the little shortcut things like that.
Yes.
Okay.
Yeah, because it's a 1 over, in this case you have to add. If it was just a centimeter cube to a meter cube, then you would subtract. Yeah.
Meter. Okay.
Yeah, but since it's 1 over, then you have to add it instead. Yeah.
Okay.
Good. Yeah, so n in this case is 8.47 times 10 to the 28. Good.
Cool. Yeah, we're just using that current form, or like the current version of the current density formula.
Okay.
No, I phrased that wrong. But the I equals Qn drift velocity times the area, and then solving for drift velocity.
Yes. Yeah, that's fine. Yep. Yep.
Area is pi r squared.
There we go.
Okay. Did you guys get it?
Nope. Yes,
I'm
I'm entering
good.
it in.
Okay.
-4 times.
Hey, it's me again.
Hi.
How are we doing?
I think I'm all good. The only question I have, because I got the answer you got for the power loss part E, is how is watts a rate? I know that we moved from like watts to kilowatt hours in one of the other examples, but it
Yes.
asks for the rate at which energy is like lost or thermal energy will appear.
Right. So remember, power by definition is the rate at which energy is converted from one type of energy to another. So it is the change in energy over the change in time. So that's what makes it a rate.
So it is a rate. Okay.
It is a rate. Yeah. So by its definition, it's a rate. Yeah.
It's just when we're multiplying amps by volts, I'm like, how? There's no seconds anywhere. There's no time.
Well, remember, an amp is a coulomb per second. So that's where the seconds comes from.
So we've just left that embedded somewhere far behind.
Correct.
Okay.
That's right. That's right. Yeah, so that's one of the things that's a little bit different with, again, as you're seeing now with electricity, is there's so many special names for things that you start to lose, kind of the notion of what all these different things are. Right? So again, when you think of velocity, you think of meters per second. Okay, so how fast is a meter changing, in a second? But again, when we think of an amp, we just call it an amp. But again, it's how fast the charges are changing per second. So even an amp is a rate. Right? So, yeah. So that's one thing that happens a lot in electricity. Because everything has its own little special name and it has its own special thing that you kind of forget, what all these things actually are, what they actually mean. But.
And especially moving through it in an accelerated fashion, it's hard to keep track of all of those.
Yes.
So I'll get done and I'll get like the number and I'm like, okay, what units is it in now? I have to double check my notes. I'm like, okay. But sometimes like you'll just get done running the calculation and you have a number, but you're like, I don't remember what unit it's supposed to be in.
Right.
And then if you've forgotten like centimeters, you're like, oh, I'm off by a margin because of that.
Right. Well, yeah, something like the exam, that's not a big deal, but something like the homework, that's a very big deal. So, unfortunately. Very nice. All right, I'll be back. Let me check on you.
I had done us and not made us do all the conversions for the given information.
Yeah, conversions can be tricky.
Especially if you like forget them all.
Yeah.
You're like, okay, we started out completely wrong. It's nice to be able to just take them in the units that they need to be in already and just kind of plug them in as you go.
Yeah. I've been trying to do that more on the exams, but these ones I can do that with, so it's fine.
Yeah.
All right, I'll be right back. Let me go check on the others.
Okay.
All right, how are we doing, ladies?
We're on the last one right now.
Good, okay. So remember, power is current squared times the resistance, or potential squared divided by resistance. So, or current times potential. So any one of those three is fine.
Okay.
So, yeah. So either I squared R, I times V, or V squared over R. Very nice.
Like it's gonna happen.
Dude, I'm like just sitting here crossing my fingers on it. We finished.
You finished? Very good.
Yep.
Yep, we're done.
Good. It's like all the other groups are almost done too. So.
We won?
Well, Katie beat you guys, and then you guys came in second. So.
All right. Yeah, she had it done, I think, already. She had it attempted, I remember last time we did group assignments.
Yeah,
but then we had
said
to
she
do the
already worked on
material.
most of it,
So
yeah,
yeah.
so she had a head start. So
that's fair. I'll take second place, I guess.
there you go. There you go.
I'm just happy we finished a group assignment in one sitting. I was just telling them that. This is like the first time I've done that.
Nice. Very nice. All right, so I'll give everybody a couple more minutes and we'll come back and we'll start the next chapter.
Okay.
Okay.
I think it's true. Slightly. But yeah, I don't know.
Okay, so what did you do? Because then whenever I do the IRMS thing, I don't do it. So is it just the current
Yeah.
time voltage?
Yeah, so he said the power will be like the potential difference of that 1.2 volts times the current that we found, but you can also do the current squared times the resistance. He said both of those work. He said like one other one, but I just heard the first two.
Yeah, IV, I squared R, or V squared over R. Any one of those.
Okay.
All right. So it sounds like you guys are pretty much all set. So give you another minute and then we'll start the next chapter.
Okay.
Things. All right. All right. All right, welcome back, everyone. So that concludes chapter 18. So we're all done with chapter 18. So now we can start the next chapter, chapter 19. So good. So next part is chapter 19. Let's talk about chapter 19. Pardon me. So chapter 19. So chapter 19 is now we're going to start looking at more heavy duty type circuits. So we're going to primarily focus on DC circuits. Okay. So remember DC means direct current. So we're just simply going to have a battery. So direct current. So first off, let's talk a little bit more about batteries and EMFs since we've been using those words all the time and we haven't really quite defined what they actually mean. So let's start off with what is an EMF? So EMF is equal to electromotive force. Electromotive force. So basically an EMF is a fancy word for pretty much anything that converts some other type of energy to electrical energy. So this is what an EMF is. So an EMF is anything which takes some other form of energy and converts that to an electrical energy. So for example, it could be mechanical energy. So I could just rotate a crank. That crank could be converted into electrical energy. This could be a waterfall. So in that case, it's also mechanical energy. The waterfall comes down, causes the turbine to move. Could also be nuclear energy, could be chemical energy, could be all kinds of different things. So it's just any other form of energy which is then converted into electrical energy. So typically these are going to be things like batteries, generators, nuclear power plants, etc. So again, anything that converts into electrical energy. So typically there are two different types of EMFs. There's what's called an ideal EMF and then what's called a non-ideal EMF. So an ideal EMF is something which maintains constant potential potential difference at all times. So in this case, if I was looking at my, say, battery, so here's my battery, inside of here, we just have simply the positive, we have the negative, and then if we measure the potential difference across here, so let's say if I measure the difference between point A and point B here, so that the change of potential across A and B would then be equal to what we call the EMF, so just the power of this thing. So even if I connect this to something like a resistor, so that I have current running through the circuit, so this is with no current, even when I run current through the system, in this case, the potential difference is still just simply equal to the EMF. So in this case, the ideal battery or the ideal EMF maintains the same potential difference at all times, even if I have this thing running current through a resistor. But of course, in reality, as we kind of talked about when we talked about with batteries, a non-ideal EMF is something which the potential difference does not stay fixed when I start running current through it. So in this case, if I initially hook this thing up with a positive and negative, so that there's no current running through my system, then again, my potential difference across A and B, so difference between B and A, is then equal to the EMF. So again, this has exactly the same amount of EMF. And again, this is with no current. But what will happen is if I now hook it up and I start running current through it by connecting it through a resistor, what happens in this case then is that the potential difference becomes less than that of the EMF, which is what we saw in the lab, right? This is now less than the EMF. So the way we usually deal with an ideal or non-ideal battery is we say that, okay, let's pretend that our battery is actually connected to a resistor on the inside, which is what we call the internal resistors. So little r here is what's known as the internal resistance. So we say is that resistance, that a non-ideal battery or a realistic battery, also being a realistic battery, is a EMF which is attached in series with an internal resistor. So in this case, our change of potential across the battery then is going to be equal to the EMF minus then the current times that internal resistance. And this is when the battery is discharging. So when I connect it to a circuit, I'm actually discharging it. Now, if I was charging the battery, this would actually be opposite. So if I was charging the battery instead, I would have current actually running in the opposite direction, actually going into the positive sign and out through the negative sign. So if I was actually charging this, in this case, this would become positive I times R. So in this case, I would be actually charging the battery instead. So when you charge the battery, you actually force the current to go through the battery in the wrong direction. So you force current through wrong direction. So instead of having it go from the positive through to the negative, it would actually go from the negative and through the positive. So you'd actually run it through in the opposite direction. So this is the mysterious EMF that we've been talking about. Again, it's just a fancy term for anything that's a battery or a generator or a nuclear power plant, whatever it is, but it's just something which converts one form of energy into electrical energy. Now here, don't let the force kind of throw you off here. This is not a force, but this is still a potential. So this thing is still a potential difference. So by definition, what the EMF actually is it's equal to the work done by the battery per unit charge. This is how we actually define the EMF. So this is the work done by the battery per unit charge. So remember that potential energy, let's see, yeah, is equal to, so actually let's write it this way. So remember potential energy, actually change of potential energy is equal to negative of the work, but we know change of potential energy is the same thing as the charge times the change of potential is equal to negative of the work, which means that the change of potential then is equal to the work done by the charge. So the EMF here is simply just a change of potential. So again, even though it has force within the name of it, it's not actually a force, it's still a potential difference, and it's still something which is driving and causing work to be done by this particular battery. But again, EMF is just any fancy thing that just converts one type of energy to another type of energy. Now, EMF can also be something that does direct current, or it could be alternating currents. As we talked about last time, we did talk about sinusoidal alternating currents. So EMF can be either one, can be direct current or for alternating currents, but we're going to focus on for now just direct currents. Okay. So good. So we're going to be looking at all kinds of crazy systems where we're going to have things like, for example, I'll have a battery attached to, say, a resistor. which might be attached to another resistor, which will be attached to another resistor, which will then be attached back to the battery. So we're going to start adding these things together in parallel and series. Right? So as we talked about with the lab, the reason that we add these in parallel and series is because, practicality speaking, we can only manufacture a certain number and certain types of resistors. So if I want to create a new type of resistor, I have to connect these guys in parallel and series. So even though we talked about this in lab, let's actually formally talk about it now. And how do we add these guys together? So how do we add resistors in parallel and series? So how do we do this? So good. So let's actually draw this. So let's say I have a battery. Here's my battery. And we're going to first look at series. Okay, so let's say I have 3 resistors connected in series. And I want to know what is the equivalent resistance of all 3 of these guys added together. So let's say here's R1, R2, and R3 connected to the battery, which has delta V. So what I want to do is combine all these guys down into one equivalent resistor. So this whole system is replaced by one particular resistor, which we're going to call REQ. And just a reminder, these squiggly lines here are what we call resistors. Okay, and that's how we're going to draw them in our circuit diagrams. So good. Let's talk about it. So what we know is that what? Here, since we have resistance, we have a potential, we also have current. So we're going to have current I, which is running through the circuit. Now, since all of these are connected in series, what that means is that the current which runs across the resistor R1, the current which runs across the resistor R2, and the current which runs through R3 are all exactly the same. So conservation of charge, i.e. conservation of current, tells us that since all of these are in series, the current has to be identically the same. So for series, conservation of charge tells us that the current is the same. So anytime we have these guys connected in series, the current must be the same. Okay. Well, what's going to be different is Ohm's law then tells us that the potential is equal to the current times the resistance. So if all of these have exactly the same current, but they all have different resistances, then they all have to have different potentials. So the potential difference across 1 is different than the potential difference across 2, which is different than the potential difference across 3. But what has to be true, though, is that the potential which is given by the battery, remember the point of having a resistor is to create a potential drop. So as the current then goes from point A here to point B, the potential has to decrease by an amount of Ohm's law. Which means that if I start off with a particle moving here, it goes through my system, by the time it gets back to the battery, it has to have lost all of the potential which was given by the battery. Which means that the potential drop here, plus the potential drop here, plus the potential drop here must sum together to equal the total potential which was gained by the battery. So what has to be true then is that the potential drop from the first plus the potential drop from the second plus the potential drop from the third must equal the potential which was given by the battery. This has to be true. This comes from conservation of energy. So conservation of energy says that whatever energy is given by the battery has to be lost by those 3 resistors. So according to Ohm's law, what this says then is that the potential drop from resistor 1 then is simply going to be the current times the resistance R1. Potential drop across R2 is going to be the current times R2, and the potential drop across the third one is going to be I times R3. Now our statement here is that what? This circuit here is identically the same as this circuit here, which means this current which is running through this circuit is exactly the same as this current running through this circuit. So that means the potential drop across this resistor has to equal the potential drop across the battery, which has to be the same as all the sum of these potential drops. So all that is saying is that the right-hand side here is going to be replaced by the current times the equivalent resistor. Okay. So since all these i's are the same, I'm going to factor it out. So this says that the current times R1 plus R2 plus R3 must then be equal to the current times the equivalent resistor. Since this current is the same as this current, we can cancel those out. So this says that the equivalent resistance is simply equal to the sum of all of these resistances. Or in a general sense, this is equal to the sum over I of Ri. So this is the equivalent resistance when they're in series. So for resistors in series, we simply then add all the resistances together. Okay. So this is the equivalent resistance. So what's the effect of this? The effect of this is to increase resistance. So if we wanted to make a resistor which had a larger resistance than the resistors that we had, we simply sum them together or add them in series. That then creates a larger resistance. So by adding them in series, we create a much larger resistance. So the effect of this is to increase resistance. Okay. So again, this is when they're in series. What happens when they're in parallel? So let's look at parallel. So for parallel, again, I have my battery. I'm going to attach that now to, again, 3 resistors. We're going to have one up here, one through the center, and then say one down here. And again, I'm going to connect these back to my battery. So this is delta V. This is R1, this is R2, this is R3. Now the difference here is the presence of these points here. So these points are points which are called nodes or junctions. This is called a node / a junction. So this is a junction point or a node. So the junction point represents a point where the current, which is coming out of the battery, so let's say current I is coming out of the battery, the current has options. It can either go through this top portion, or it can go through the middle portion, or it can go through the bottom portion. So some of the current might go through in this direction, so this might be I1. Some would go through the center, so it's going to be I2, but some might go through the bottom path, I3. But what has to be true is that the current I1 plus the current I2 plus the current I3 have to sum to the total amount of current which is coming out of the battery. So in this case, what has to be true is that I1 plus I2 plus I3 must equal the total current coming out of the battery. And again, this is just conservation of charge. Saying now we're not losing any charge and we're not making any charge. All the charge is here. So now since this current here is different than this current, which is different than this current, they all have different resistances, but it turns out what is actually the same is now that in parallel, they don't have the same currents, but they actually all have the same potential. So in parallel, what's the same is the potential. So potential is the same. So why is that? Well, that is true because if I look at my circuit, so let's say it starts here, and then I include only this portion, which is the bottom portion, and I come back around to the battery, well, again, conservation of energy says that whatever potential I give here, I have to lose here, which means the potential drop here must be the same as the potential drop here. Or I could go through the center one, so I could start here, go through the center one, go back through the battery. So again, conservation of energy says whatever potential my battery gives, I have to drop through this resistor. So this potential drop here has to equal that of the battery. Or I can start off here and go through the top portion, down through the battery. In that case, again, conservation of energy says whatever potential I gain from the battery has to be lost through this resistor. So this also has to have exactly the same amount of potential. So in parallel, conservation of energy tells me that the potential across each one of these different resistors has to be the same. Okay? So this potential here has to be the same as this potential here, which has to be the same as this potential here, which in this case has to be the same as the battery itself. Okay? Now, we're going to use that here when we go back to Ohm's law. So remember, Ohm's law again says that the potential is equal to the current times the resistance, which means the current then is equal to the potential divided by the resistance. So this means that I1 I could rewrite as the potential divided by the resistance R1. I2 then is the potential divided by the resistance R2. I3 then is the potential divided by resistance R3. And our claim is that we're going to collapse all of this down to create one equivalent resistor, which again we're going to call REQ, which again has the same amount of current which is coming out in this direction. Okay. So here, we can now say that the current is going to be equal to the change of potential divided by the resistance, REQ. Okay, this is our claim. Now, since this potential is the same as this potential, the same as this potential, which is the same as this potential, all the potentials are going to cancel. So this tells me that 1 over the equivalent resistance then is equal to 1 over the resistor R1 plus 1 over the resistor R2 plus 1 over the resistor R3, or in a general sense, this is equal to the sum over all the inverse resistances. Okay. So for resistors in parallel, we add them all inversely together. What's the effect of this? Well, the effect of this then is to decrease the resistance. So when you add resistors in parallel, you actually decrease the overall resistance of the resistors. So when I add all 3 of these in parallel, that's to create a resistor which has less resistance than any one of these. That's the overall effect of doing that. So if I want to have a larger resistance, I add them all in series. If I want to have a less resistance, I add them all in parallel. Okay, that's the overall effect. So this is how we actually add resistors together. So again, we add them either in series. In series, we simply sum them all together. In parallel, we add them inversely. But the effect of doing this is to either increase the resistance or decrease the resistance. So let's use all this and let's do an example. And so this says that in the circuit below, what is the equivalent resistance? What are the currents flowing through each of the different resistors? And how much power is delivered by the battery? And finally, how much power is lost by each one of the resistors? So this is what we want to know. How much time we got? 10 minutes. Okay, good. Should be enough time. Now, we did this in lab, but again, we're going to become more familiar in how to do this. So these problems are kind of tedious, but they're easy simultaneously. Okay. So they're tedious in the fact that what we have to do is first collapse all of this down into one equivalent resistance. So here what we're going to do is we're going to add these 2 together, which are in parallel. And then we're going to add this one to those 2, which are now in series with this one. So we have to first collapse everything down into equivalent resistor. Once we do that, we then have to determine the currents and all that different stuff. And then we have to unravel what it was that we just did using what's the same as we go through. Okay. So I said, so this is kind of tedious, but not too bad. Okay. So let's redraw our circuit here. So let me use my black again. So here's my battery. This is delta V. This is attached in series to R1. And then R1 is attached in series to R2 and R3, which are in parallel. R3. And then these guys are now attached to the battery. Okay? So the first thing we have to do is identify what's in parallel and what is in series. So in this case, we can see that R2 and R3 are actually in parallel. So these guys are in parallel. So once I collapse these guys, which are in parallel, then those 2 are together with R1 in series. Okay. So what this means is first we're going to collapse R2 and R3 together into an equivalent resistor, so that this is now R1, and this is now in series with R23, which R23 is the equivalent resistor from R2 and R3. Now, since R1 is in series with R23, we're going to collapse these two down into finally our equivalent resistor, which is REQ. Okay, so this is REQ. And this is our delta V. Okay. So delta V was what? 120. R1 was 400, 500, and 700. Okay. So 400, 500, and 700. Okay. Now, once we get here and we actually calculate REQ, now we have to start going backwards to see where it is we came from and use what's in the same. Okay. So that means then if I want to know what's the same here, well, REQ came from two things which were in series, and I know current is the same in series. So that means whatever current is running through here, let's call that IEQ, has to be the same current which is running through this one and also running through this one. Now, since I know IEQ and I know R23, I can find the potential, so I can see where R23 came from. So I go backwards again, and I see, well, R23 came from two which were in parallel, which means that I know what's in the same in parallel is potential. So the potential across R23 is the same potential which is across 2, and the same potential which is across 3. Okay. So this is what kind of makes it tedious. So we have to go all the way forward and then all the way back. All right. So first we have to combine everything together, and then we have to unravel it back up. So it's kind of like Christmas time, right? Where you have to first wrap a present, and then somebody has to unwrap that present. Okay. So let's think about it that way. So good. So let's do all the math for it. So first things first is we know R23 came from two things which were in parallel. So we know in parallel we have to inversely add these together. So that becomes the same thing as R2 times R3 divided by R2 plus R3. So that's adding those guys together. So that's the same thing then as what? 500 times 700 divided by what? 1200. One. And then finally REQ came from two things which were in series. So that becomes R1 plus R23. If I add those together, that is then 400 plus whatever that answer is. Add those together, if I remember right, this works out to be about 691 point something. So 67. 91.67 ohms. Okay. Always okay? Now from here, we can now find IEQ. So Ohm's law says that the change of potential, again, is going to be equal to, in this case, IEQ times REQ, which means IEQ then is going to be the same thing as our change of potential divided by REQ. So here, we know our potential is 120 volts divided by REQ, which is 691.67, which then is IEQ. Put in our numbers, we find in this case is this works out to be 0.173. So this is 0.173 amps. So this is our IEQ. Now again, from here, we would go backwards. So now we said, okay, REQ came from two things which were in series. We know in series, they have to have the same current. So that means the current which is running through R1, which we're going to call I1, is simply the same amount of current as IEQ. So this means the current I1 is equal to IEQ, which is then equal to 0.173 amps. But since these are in series, that means that the current running through R23 is also IEQ. So now that we know the potential, or sorry, now that we know the resistance, we also know the current, we can now find the potential. So if I plug in my numbers, I can now find that amount of potential. So in this case, this is going to be equal to 0.173 times whatever number this happens to be. Okay. Now, Since I now know the potential, I know that R23 came from two resistors which were in parallel. So now what I know is that this potential here and this potential here are exactly the same. So the potential which is across 2 is that potential V23, and potential across 3 is also that potential V23. So now, since I know the potential and I know the resistance, I can now find the current. So that means this current here, let's call that I2, and this current here, let's call that I3. So finally we have I2 then is going to be equal to the potential, so delta V23, divided by the resistance R2. Plug our numbers in this case, what we get is that this works out to be 0.101 amps. So 0.101 amps. Then the current I3 is then equal to delta V23 divided by that resistance R3. So that means I3 then is going to be equal to 0.072 amps. 0.072 amps. And just as a check, what has to be true is that the current I2 plus the current I3 has to equal the current I1, because again, I1 is coming in, splitting up into I2 and I3, but then it has to recombine back to I1 to come back through. And we can see here that if I take 0.101 plus 0.072, that is indeed the same thing as IEQ. So those currents do add together. So this is a nice quick way to check to make sure that we didn't make any mistakes. Always okay? So good. So that's REQ, and then those are the currents through each one. So the next part then says, what is the power which is delivered by the battery? Okay. So good. So we know that power, which again is the rate of energy, is equal to either the current times the change of potential, the current squared times the resistance, or the change of potential squared divided by the resistance. Now, when it comes to the battery, it doesn't make sense to talk about resistance because we don't talk about resistance when it comes to battery. So when it comes to the battery, the one that we care about is this one, the top one, I times the potential. So in this case, the power delivered by the battery then is going to be the current times the change of potential from the battery. Now in this case, the current which is going through the battery is simply I1. So what we care about is not just any random current, but we care about the current which is coming directly out of the battery, and that current is what we call IEQ or I1. Okay? So the current which is running through the battery itself is I1. So it's going to be the same thing as I1, which is 0.73 times the potential, which was what, 120 volts, right? So plugging our numbers we find in this case then is that works out to be about 20.82. So this is 20.82 watts. Power lost by the first resistor, which is the next part. Then we can use the second equation. So here we can say this is I1 squared times R1. So it's going to be 0.173 quantity squared times R1, which is 400. So the power which is lost through that resistor then is going to be 12.04 watts. Power through the second one is going to be I2 squared times R2. So it's going to be equal to 0.101 squared times R2, which is 500. So in this case, the power lost by that one is 5.12. So 5.12 watts. And then finally, the power lost by the third one is then equal to I3 squared times R3. So that's going to be 0.072 squared times 700. So the power lost through the third one then is 3.66 watts. Okay. And again, just as a check, what has to be true then is the power delivered by the battery must equal the sum of these three powers. So the power which is lost by the first resistor plus that of the second plus that of the third has to equal the total amount of power which is being supplied by the battery. So if I add these three together, I can see that, yes, it does equal to 20.82. That's okay. So, like I said, these are kind of easy, but it's also tedious, especially when you have more than 3 or 4 or 5 numbers of resistors, where you have to combine all these things down and then find an equivalent resistance and an equivalent current, and then unravel everything that you did. So one thing to get into a good habit with is do exactly what I did here, which is draw pictures. So anytime you collapse something down, so here when we collapse these down into parallel, draw the picture. And then when you collapse these, draw another picture. So that way when you're going backwards, it's a lot easier to track what it was that you did. So again, that way you can see, well, this one came from 2 things which were in series. What's the same? Current. This came from 2 things in parallel. What's the same? Potential. And then just keep going back that way. So yeah, so when you're doing these types of problems, definitely make sure you draw the pictures and put the arrows so that way you know you went from here to here to here. That way when you're backtracking, you know exactly what you did and then how to unravel it. And then what's the same. So here, if you notice, the only equations we're using are Ohm's law and then how to add these things in parallel and series. That's it. So when I'm unraveling what I did here, it's just applications of Ohm's law, just depending on what it is that I'm looking for. Okay. So, like I said, these are pretty easy, but they're also tedious. So you just have to make sure you keep track of everything. But it's, you know, once you kind of get used to it, it's not too bad. Okay. So good, we are out of time, so we'll stop there. So tomorrow we will start off with another group assignment, which deals with adding these things in parallel and series. And then from there, we'll talk about how to add capacitors in parallel and series. And then basically do all this all over again with capacitors. Okay. And then we'll make it a lot more difficult. We'll start looking at what's known as Kirchhoff's loop rules, which is adding multiple batteries with multiple stuff all going on. So life will be great. Okay. So any questions on any of this before we call it a day? No, it's okay. All right. Well, then I'll see everybody tomorrow.